right, greetings YouTube, beautiful mind here, and so we're this is Mr. Pfeiffer. We are doing going to go ahead and move into our next topic. Let's see if there are a few announcements. So a few announcements for my students. Three key points. The first thing is that be sure that you're affording your Be sure that you're forwarding your GMC email to an email that you check regularly. The main way that I communicate with you all is via your GMC email. So if you've missed anything, or if you feel like you've missed any announcement, you want to go to the announcements tab in our Moodle page and just read through those announcements. Everybody should have Another thing is everybody should have full access to Pearson. Okay. I'll be going updating my grade book if I see that anybody doesn't have full access, or if I feel like somebody's missing something or something of that nature. I probably will be reaching out to you. The grades are in for week 2. I just have to update the Moodle grades so that you can see it. Let's see. This week we're going to be on the lookout for a quiz. Okay. We took exam 1 over the weekend, and we did quiz 1 on week 1. So this is week 3. We're gonna have a quiz this week. Next week is spring break. Okay, so do the best you can with it, with this work, and work hard, but then take a break. Like with all the stuff that's going on, just take a break next week. Like do whatever you feel like you need to do, but get your rest, play. We can't really do too much, so just try to relax and get your mind right. Just kind of recover. But this is about the rhythm that we're gonna have all the way through the end of the quarter. Our assignments are on Pearson. So that's the second thing that I wanted to mention. Just be sure that the main thing is that we're submitting our assignments promptly on Pearson. Keep in mind, we get unlimited attempts at these assignments. Okay, so that means you can get whatever score you want. If you don't have the score that you want, I mean, you could just take it again. Like I'm intentionally giving you unlimited attempts. Okay, um, and also with any assignment, we can actually submit them past the due date. But there'll be a penalty. So like any assignment submitted past the due date, the highest that we can make on it is an 80, which is a low B. And right now I'm still okay with the notion of submitting exams past the due date, but the highest we can make on an exam submitted past the due date is going to be a 79, which is a high C. Okay. So the best thing is, if you want to really maximize your score, you want to get these assignments submitted before the deadline is, as best as you can. Let me see if there's anything else. So yeah, attendance credit is going to be based on, you just have to submit 1 assignment per week to get attendance credit. And then obviously if you're watching this video, you're already made your way to my YouTube channel. But go ahead and subscribe to my YouTube channel and turn your notifications on. This is where I'm going to be posting video responses and live lectures. So then as long as you have your notifications turned on, when I go live or if I post a video response, I try to make a relevant title. So then when you see that title, you're like, oh yeah, I had that same question. And then you can just watch the video, or, oh, this is the lecture for this course. Let me go ahead and, watch that. Or at least it's just about awareness, as long as you know it's there. Okay. I can't think of anything else. There is I think it's a participation and honesty quiz that's on Moodle. Go ahead and take that. I think that's due by the end of the week. Okay. So we want to be sure to go ahead and submit that assignment. And we'll be ready for exam 2 when we return from spring break. I can't think of anything else. Let me see. So I'm gonna turn this on. Do the following. Okay. So with that being said, I can't think of anything else. So we're gonna actually continue with our lecture for today. There it is. So I think last time we did section 3.1, basic concepts of probability and counting. So today we're going to move into section 3.2, conditional probability and the multiplication rule. Okay. My goal for this week is to go ahead and finish out chapter 3. Okay. So section 3.2, conditional probability and the multiplication rule. Some objectives here are how to find the probability of an event given that another event has occurred, how to distinguish between independent and dependent events, how to use the multiplication rule to find the probability of 2 events occurring in sequence, and to find conditional probabilities. Do we have that laser pointer here? Let me see. I say we have a pen. Let me see, what else do we have? I guess I can use that. That'll work. Those are notes. What is this? Oh, okay, I see what that does. And these are just some notes. Okay. All right. Let me see. Does the pen work? Okay. Sorry, I was just playing around with the settings. So I'm using a little bit different. Instead of using my note-taking software, I'm going to use PowerPoint for this presentation. So that's why I was just pausing for a moment to get a feel of the controls they have here. Okay. So conditional probability is the probability of an event occurring given that another event has already happened, right? It's going to be denoted. Let's see if we can read this properly. So I'm going to go, let's go like this one. That should work. Okay. So this is denoted in the following. And it's red. It's the probability of B given that A has already occurred. So that vertical bar here um, is our given, is read as given, is our given symbol. So let's read that one more time. It's going to be the probability that the event B occurs given that the event A has already occurred. Okay, that's fine. All right, I'm gonna go like this. So let's look at this example on finding conditional probabilities. What's the time? Okay. So two cards are selected in sequence from a standard deck. We're asked to find the probability that the second card is a queen, given that the first card is a king. Assume that the king is not replaced. Okay, let's look at this again. So it says two cards are selected in sequence from a standard deck. Find the probability that the second card, okay. So we're asked to find the probability that the second card is a queen, given that the first card is a king, all right? So now, let's think about this. Okay, so we're given that the first card is a king. So now we're on the, let's start from the second draw, right? We want to find the, I think that's how this goes. Let me think about it. Give me a moment. Yeah. So if we have a standard deck of cards, a standard standard cards, blah 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 blah, a standard deck of 52 cards, how many queens are there in a standard deck of cards? Well, there are 4 queens in the standard deck. Now, in the standard deck, we're going to have 52 cards initially. Keep in mind that this is the second draw, so how many cards remain? So in the first draw, if we drew a king, that means now there's only 51 cards remaining. So then whatever 4 divided by 51, that's going to be our result. Okay. So because the first card is a king and is not replaced, the remaining deck has 51 cards, 4 of which are queens. So then the probability the second card is a queen, given that the first card is a king, is going to be 4 out of 51, and you see it there. Okay. Let's try another example. Give me just a moment. All right, and we are back. All right. So let's look at this example. It says the table shows the results of a survey in which 2276 social media users were asked whether they have ever been offended by something they saw on social media. Find the probability that the user is male, given that the user was offended by something on social media. So for this probability, what we're going to do, we're going to say the number of outcomes in our event over total number of outcomes. It says find the probability that the user is male. But if it says given that the user was offended by something on social media, so we have to restrict the discussion to the person being offended by something on social media. So we're going to restrict it to this column. Okay. So we're going to restrict it to this column. So then how many of these users are male? We have 532 out of a total of 1151. So then it should just be the 532 over 1151. Okay, and I'm going to clear those markings. Give me a moment again. All right, we're back. Okay, let's just try the next one. So independent events, this is going to be the occurrence of one event. This is going to be occurrence of one of the events does not affect the occurrence of one of the events does not affect the probability of the occurrence of another. So in the case of conditional probability, the probability that B happens given that A has already happened is just going to be just B, right? So if these events are independent, that means that A does not affect the probability of B at all. So then this conditional probability collapses to just the probability of B. And if we reverse the order, then it becomes just the probability of A. Okay. Events that are not independent are dependent. Okay. So we're asked to decide whether the events are independent or dependent. The first event is selecting a king from a standard deck of 52 playing cards, not replacing it, and then selecting a queen. So we have the first event and then the second event. Let me think about it. Okay. So we want to see if these events affect each other, right? So let's start with the conditional probability. So let's find the probability. Let's find the probability of getting. Let me see. Pulling a queen, given that we've already selected a king, right? So I think we did this one earlier. The probability of getting a queen, we have 4 queens at this point, and we've drawn a card, and the first card was a king, so that means we have 51 cards remaining. Now, if these events are independent, this number would actually be the same as just the probability of B, right? But if we look at the probability of getting a queen by itself, we have 4 queens out of a total of 52 cards. Notice that 4 out of 51 is not equal to 4 out of 52. So that means that the probability of B given A, or the conditional probability of B given A, is not equal to just the probability of B. So that means that these events are not independent. That's right. Malachi's like, amen. That's right. She's chiming in. She said, that's right. She is fast. I swear this dog can teleport. She had to be 30, 40 feet away from me. And then as soon as I say her name, in an instant, she was right here. I can't see her because it's dark. But she was like over there by the door. I say her name, and now she's like trying to get some attention from me. In an instant, though, I was like, I don't know how she got over here so fast. I didn't see anything. All I know is 1 minute she was over at the door barking. Next thing I know, she's right up on top of me. I'm like, how did she do that? This dog is crazy fast. Anyway, all right, so she is joining us now. All right. So the conditional probability is not equal to the probability of the second of B. So then these events are not independent, so these events are dependent. I think I'm going to clear these pin markings. So we're going to say, so the probability of B given that A has occurred, the second card is a queen given that the first card is a king, was 4 out of 51, but the probability of pulling a queen by itself was 4 out of 52. So because these two numbers are not equal, the occurrence of A does change the probability of the occurrence of B. So one event does depend on the other. Okay. So we're asked to decide whether these events are independent or not. So if they are independent, then the probability of B given A is going to be equal to just the probability of B. So in this one, we have tossing a coin and getting a head, and then rolling a 6 and getting a die. So first, let's consider the probability of B given A. That's going to be the probability of rolling a die and getting a 6, given that we tossed the coin and flipped a head, right? So then rolling a 6. How many 6s do we have on a die? We have 1. The probability of that occurring is going to be 1 out of 6. And then, which is the same as just the probability of B by itself, all right? Because tossing the head does not affect what number we get on the die. So then we're going to say that these events are independent. I'm going to clear the ink. So the conditional probability of rolling a 6, given that we got a head on the coin, is 1 out of 6, and the probability of rolling a 6 by itself is also 1 out of 6. So then we say these events are independent. One does not affect the probability of the other. Okay. In this example, we're asked to decide whether the events are independent or dependent. Driving over 85 miles per hour and then getting into a car accident. So we're gonna have to just use just logic here, really. So if we consider the conditional probability of B, given that A has already occurred, let me see. So the probability of getting an accident, given that the person is driving over 85 miles per hour, you could imagine that, going at that speed would influence the chances of someone getting into a car accident. So we would say that these events are dependent. Let me see. Am I thinking? Yeah, that's about the best we can do there, right? So driving over 85 miles per hour definitely increases the chances of getting into an accident. Okay. So next we'd like to talk about this, the multiplication rule for probability of A and B. The probability that two events A and B will occur in sequence is going to be given by, we have the probability of A happening and then B happening is going to be the probability of A times the probability of B, given that A has already occurred. So we have one event and then a second event occurs. It's going to be just the probability of the first event by itself times the conditional probability of the second event, given that the first event has occurred. If the events are independent, then this rule becomes just the probability A, and the conditional probability condenses to just the probability of the second event because the first one doesn't affect the second one, right? So that's kind of how we do that. Okay. This can be extended for any number of events in sequence. So 2 cards are selected without replacing the first card from a standard deck of 52 playing cards. Find the probability of selecting a king and then selecting a queen. Okay, I'm going to write it like this. So we're asked to find the probability of selecting a king and then a queen, right? So this is going to be the probability of selecting a king times the conditional probability of selecting a queen, given that we've already selected a king. And so my dog is like extra cuddly now because, you know, she got a bath yesterday, so she don't know how to act now. It's like people aren't pushing her over like, "Ugh, you stink, get away from me." Now we're like, I just want to eat you. Nom 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 nom. Obviously, we're not gonna eat our dog, but yeah. So she's like extra cuddly now because she got a bath yesterday. It's too funny. So yeah, and it's funny because like I take like the tall kitchen trash can, the recycling bin that we have, and like I just start filling it with like water, and so she takes like a standing bath, and that just seems to be the easiest way because then she's a little chihuahua, so she be like gripping onto the edge of the trash can and it's full of water, so she can't really move it around, and then so she's like taking a standing bath, and it just works, and I'm like okay, and then I just take the water outside and dump it, and we're good to go. So now she's like nice and clean. All right, so let's go through this. I'm going to continue working over here. So what's the probability of selecting a king? We have 4 kings. Go ahead. You got to make up your mind what you're going to do. Thank you. But don't start making noise. I know you need to go to the bathroom. You're going to have to let me, I need to finish this and then we can go outside. Okay. So how many kings do we have? We have 4 kings at this point out of a total of 52 cards. We're going to say times. So now we're not putting that first card back. At this point, we have 4 queens, but there's only 51 cards remaining, right? And then whatever that number is. 4 times 4 divided by 52 times 51, okay? And you see it here. All right. She's trying to gear up. She's saying me, 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 me. She's trying to gear up for distractions and attention. I know she likes to go out there. She wants to chase like squirrels and anything that moves. It's so funny because like she'll just sit there and stare outside, and then sometimes she'll start like huffing and puffing. She'll be like, she'll like start like, hey, oh, I didn't want to show that. She'll be like, hey, who's there? And it's like a squirrel just sitting there in the yard looking at her like, yeah, you can't get me. So what you gonna do about it? Like I'm just out here. You know, I'm just a squirrel looking for a nut. Like, you know, he's just out here. So it's just so funny. And she be like losing her mind. And then like when I open the door, she goes bounding as fast as she can trying to catch one, but she never catches them. They're way too fast and they just scurry up a tree. And it's nothing she can do about it. It's so funny. So anyway, a coin is tossed and a die is rolled. Find the probability of tossing a head and then rolling a 6. Okay. So we're asked to find the probability of tossing a head and then rolling a 6, right? Okay, so we just said that this is going to be the probability of the first event times the conditional probability of the second event, given that the first event has occurred, all right? So let's see, the probability of getting a head is going to be 1 out of 2. We have 1 head out of 2 options times now we said that these events are independent, so the second one actually collapses to just the probability of getting a 6. So we have 1 6 out of a total of 6 options. So then this result is going to be 1 out of 12. Okay, let's see, how do we do? You see the 1 out of 12 there. Okay, and again, the second one condensed to just the probability of 6 because these events are independent. For anterior cruciate ligament reconstructive surgery, the probability that the surgery is successful is going to be 95%. Find the probability that 3 ACL surgeries are successful. So we're asked to find the probability that the first event is successful, and then the second event is successful, and then the third event is successful, right? So this is going to be the probability that the first surgery is success times the probability I'm going to put a 1 for the first surgery, times the probability the second surgery is successful given that the first one is success. And then we're going to say times the probability that the third surgery is successful given that the first and the second were successful. Kind of out of space, but that's okay. But keep in mind, now, should one surgery affect the next person's surgery? No, these events are supposed to be independent, right? Because these events are independent, all of that actually collapses to just the probability that the first event is successful times the probability that the second surgery is successful times the probability that, oh, that's supposed to be a P. So let's go like this. Probability that the second surgery is successful times the probability that the third surgery is successful, all right? But then what's the probability that each surgery is successful? Well, this has a probability of success of 95%. Each of these do. So then it's just going to be that number to the power of 3. Ugh. And then whatever that number is. Okay, I'm going to clear these markings. Okay, you see it there. What's the time? I don't even know what time I started. I think it was about 7. Do I have my stream time here? Okay, well, I'm not going to worry about it. Okay. So moving along. Find the probability that none of the 3 surgeries are successful. Okay, let's think about this. So we want the probability that the first is a failure, and then the second is a failure, and then the third is a failure, right? So again, because these events are independent, we can just kind of jump to the following idea, is that this is going to be the same as the probability of the first one being a failure times the probability that the second one is failure times the probability that the third one is a failure, right? So then if it has a 95% chance of success, that means it has a 5% chance of failure. So we're going to say 0.05 to the power of 3. Okay, and then whatever that result is. I'm going to clear this out. And you see it there. So it has a low chance that all 3 are not successful. All right. Find the probability that at least one of the 3 surgeries is successful. Let's see this one. Okay. So we just found so this will be we could either have what? 1 successful surgery, or 2 successful surgeries, or all 3 could be successful, right? That's if we were going to calculate each of those. But instead, the analogous is that, you know, we could also talk about 0 of the surgeries are successful. So instead of calculating 1 or 2 or 3 and adding those up, we can actually use what we just found, that none of the surgeries been successful. So for this one, this is, let me see, the probability of at least 1 successful. So the probability of at least 1 successful is going to be the same as 1 minus the probability of none of them being successful, which we just found. So that's going to be 1 minus 0.05 to the power of 3. and that's like 0.999. Let me clear out this ink. All right. So this is the complement rule. So we ended up using the complement rule here. Okay. So in a recent year, there were 18,187 U.S. allopathic medical school seniors who applied to residency programs and submitted their residency program choices. Of these seniors, 17,057 were matched with residency positions, with about 79.2% getting one of their top choices. Medical students rank their residency programs in their order of preference, and program directors in the U.S. states rank their students. The term match refers to the process whereby a student's preference list and a program's director's preference list overlap, resulting in the placement of the student in a residency position. Find the probability that the random selected senior was matched with the residency position and it was one of the senior's top 3 choices. Okay, so we're asked to find the probability that they were matched and it was one of their, I'm going to put T for top 3. Okay, so we just said that events occurring in sequence is going to be the probability of the first event times the conditional probability of the second event given that the first event has occurred, right? So let's kind of go back and see, can we find what's the probability of a student being matched with there being a match? So we had these 18,000 seniors. It says of these seniors, 17,000 were matched with their residency position. So then that probability is going to be that 1757 divided by the 18,187. So this number is going to be that 1757 divided by the 18,000. I think it's 18,187. Okay, so that's that probability. The probability of it being one of their top 3, given that it was already a match, if we go back, it says with about 79.2% getting one of their top 3 choices. So given that it was a match, 79.2% get their top 3. So then this probability is 0.792, right? So then we're going to multiply those 2 probabilities. Okay, I'm going to clear this ink. And you see that there. Give me just a moment. All right, and we're back. Okay, I'm going to let that be. Then we're asked to find the probability that a random selected senior that was matched to a residency position did not get matched with one of the senior's top 3 choices. Okay, so I'm just going to show this. So we're going to use the complement rule. It's going to be the probability. Let's see. So given that they were a match, it was not one of the top 3. So we're going to use conditional probability. And we're going to use the complement rule. 1 minus the probability we just found. And we get this. Is there one more? Would it be useful for a random selected senior to be matched with the residency position and it was one of the top 3 choices? Let's just look at this one. It is not unusual. Sorry, I think I said useful. It is not unusual because the probability of a senior being matched with the residency position that was one of the top 3 choices is about 74.3%, which is greater than 0.05. So by unusual, it would have to be less than 0.05. In fact, with a probability of 74.3%, this event is likely to happen, right? Okay. So let me see. That ended this session let's see. I wish I could see the time. That's the only thing I need to see. Hang tight. I'll be right back. I think what I'm going to go ahead and do, I'm going to go ahead and load, that was 3-2. Let's go ahead and do 3-3. We're only going to have one more section that we're going to need to do for the week. It's going to be 3-4. And I think that section is fairly short, but we'll probably save that for Friday. And that way we can take time to do our quiz and things of that nature. But let me go ahead and load 3-3. And we're back. Maybe that's fine. Okay, so we are moving. Did it stop the presentation view? Let me see. Let me try this. Give me a moment. There we go. And if I go like this, yes, this is exactly what's supposed to happen. Okay. So we are ready to move into section 3-3. So moving along, section 3-3 is going to be the addition rule. So some objectives here are how to determine whether two events are mutually exclusive and how to use the addition rule to find the probability of two events. We say that two events are mutually exclusive if two events A and B cannot occur at the same time. So mutually exclusive means that they cannot occur at the same time. A and B have no outcomes in common. Okay, so we're kind of discussing this via Venn diagrams. On the left, we have two events that are what we consider to be mutually exclusive. They don't share any common outcomes. Versus on the right, we have two events and they do share some common outcomes. So those events are not mutually exclusive. So then we want to look at these examples and determine whether these events are mutually exclusive or not and explain our reasoning. So event A is rolling a 3 on a die and event B is rolling a 4 on a die. What are the outcomes for event A? The outcomes for event A is just the number 3. The outcomes for event B is just the number 4. So these events is an example of something we would consider to be mutually exclusive. The first event has an outcome of just a 3. The second event has an outcome of just a 4. These outcomes cannot occur at the same time, so we say that these events are mutually exclusive. So in this next one, we have the event A is randomly selecting a male student, and the event B is randomly selecting a nursing major. So then, is it possible for these events to overlap? Can we have a student that is male and nursing? Yes. So that means that these events are not mutually exclusive. Okay. So in this next example, event A is randomly selecting a blood donor of type O, and then event B is randomly selecting a female blood donor. Can these events occur at the same time? Yeah, you could be type O and be female, so these events are not mutually exclusive. So then next we have this addition rule for the probability of A or B. So now in the last one, we had the multiplication rule where it was A and B. And so we explore how do we multiply it, like when we have events in sequence. This one is saying that the event A can happen, the probability of A happening or B happening, we're going to use the addition rule. The probability that events A or B will occur is going to be, the probability of A or B is going to be equal to the probability of A plus the probability of B minus their intersection. So keep in mind, remember when we had the Venn diagrams and we had events A and B that overlapped? The reason we were moving that, we're saying minus the intersection, is because when we count A and B, if they overlap, we're going to be counting some outcomes twice. So we need to remove one of those duplicates. In this context, to remove a duplicate, we're going to say minus the intersection, because we counted that intersection twice, right? So if the events are mutually exclusive and they don't share anything in common, then their intersection is going to be 0, and that probability is going to be 0. So that last term is gone, and we just have the first part of this formula, of this rule. This can be extended to any number of mutually exclusive events. Okay. Ooh. Ooh. All right. So we select a card from a standard deck. Find the probability that the card is a 4 or an ace. Okay, so we just introduced the addition rule. We're asked to find the probability that the card is 4 or ace. So this is going to be the probability of getting a 4 plus the probability of getting an ace minus their intersection, the probability of getting a 4 and an ace, right? What's the probability of getting a 4? How many 4s do we have? We have 4 4s out of a total of 52 cards. Plus, we have 4 aces out of 52 cards. Minus, how many cards are 4 and ace? There are 0. So that probability is going to be 0 out of 52. So then whatever 8 out of 52 is, should be our result here. It's here. Okay. So we roll a die, find the probability of rolling a number less than 3 or rolling an odd number, okay? So we're asked to find the probability of rolling a number less than 3 or rolling an odd. So this is going to be the probability of rolling a number less than 3 plus the probability of rolling an odd minus the probability of their intersection, right? Less than 3 with odd, okay? So then the probability of getting a number less than 3, well, what are those outcomes? We can get a 1 or a 2, right? So there are 2 out of a total of 6 there. Plus, probability of getting an odd, well, how many odds do we have? We have 1, 3, 5. So we have a total of 3 odds out of 6. Minus, how many numbers are less than 3 and odd? There's only one number, which is 1. That's less than 3 and odd, right? So then 2 plus 3 is 5, minus 1 is 4, which is 2/3. About 66.7%. Okay. Okay, moving along. So this example says the frequency distribution shows volumes of sales in dollars and the number of months in which a sales representative reached each sales level during the past 3 years. Using this sales pattern, find the probability that the sales representative will sell between 75,000 and 124,000 next month. 75 to 124. Let's just use this. So 75,000 is here. We have 7 outcomes there. And then for the next range, we have 9 outcomes there. And we just want either the first one or the second one. So we should be adding these. 7 plus 9, what is that? 16 out of a total of 36. 16 divided by 36. Notice that these events are mutually exclusive, so we don't have anything in their intersection. 16 out of 36. You see it there. Okay, now as you kind of watch these videos, work through these examples, if you have questions, write them down and reach out to me. Also, we have a tutor. Just let me know if you need access to them. I think I put some information in the announcements tab for that. If you don't see it, again, just reach out and just, and we'll make sure to connect everyone. Okay. In this example, it says that a blood bank catalogs a type of blood, including whether it is Rh positive or Rh negative, given by donors during the last 5 days. The number of donors who gave each blood type is shown in the table. Find the probability the donor has type O or type A. So let's see. Notice that type O or type A are mutually exclusive. They don't overlap. So then the probability of O, how many O's? We have 184 out of 409. So that's going to be 184 divided by 409 plus type A is 164 divided by 409 minus the intersection, which is 0. So it's just going to be the 184 plus 164 divided by 409. Okay. Find the probability that the donor has type B or is Rh negative. So if we look at type B and we have Rh negative, these do overlap, and it's or, so we need to use, okay, let's kind of write this one out. So we have the probability that the donor is type B or Rh negative, right? So this is going to be the probability of B plus the probability of it being Rh negative minus their intersection. I'm going to say the probability of their intersection just because I'm out of space. B and the negative, right? Don't be negative though. Well, it's not always bad to be negative. Like sometimes you want to be negative. Like in certain tests, you definitely want the test to come back negative. So it's all subjective. Anyway, the probability of B. We have 45 B's out of 409 plus Rh negative is going to be 65 out of 409 minus their intersection is there are 8 that are B and negative, so that's going to be 8 out of 409, and then whatever that result is. Okay, let's see how do we do. The events are not mutually exclusive, so they can have both blood types. So then type B was 45, Rh negative was 65, and their intersection was 8, and we get this. Okay. So this is a summary of probability. I'll let you kind of go through this on your own. Let's look at this one. Use the figure to find the probability that a running selected draft pick is not a running back or a wide receiver. Okay. So if we want the probability of them not being, let's kind of do like this, clear them. We want to find the probability of them not being a running back, or let me think about this. I feel like I'm not writing it right. Here, let's just do it like this for the sake of time. So we're going to let A be that the draft pick is a running back and B is a wide receiver. These events are mutually exclusive, so the probability the draft pick is a running back or wide receiver is this. Is that it? Okay, yeah. So this is that that they are a running back or a wide receiver. So running backs, we see here we have 23 running backs. Wide receivers, we have this. So then and notice that these events are mutually exclusive. So then we say running back or wide receiver, we just find each of those probabilities. Let me see how many we have. 253 players here. So it's going to be 23 divided by 253 plus 31 divided by 253 to get that probability. Then we're going to use the complement rule to negate this. All right. So then we have those numbers there. Then we're going to say 1 minus that to find the probability of them not being either of those. We get this, okay? And that brings us to the end of this section as well. I got half a mind to just go ahead. Let's just power through, right? So let's just go ahead and power through, and let's go ahead and load. Go ahead and do section 3-4, and that way, Friday I'll just be available. I mean, I'm pretty much available during class time every day anyway right now, but it doesn't. We might as well just go ahead and do the last section, so that way we'll be done for the week. Okay. Keep in mind we do have spring break next week. We can anticipate a quiz this week. I'll get that up as soon as I can. All assignments are due Saturdays at 11:59, and you can work on them past the deadline, but there'll be a penalty. The highest that we can make on any assignment will be 80%, and the highest on an exam will be 79%, which is a high C. Okay. So give me a moment to just go ahead and load 3-4. All right, and we are back. Okay. So let's go ahead and take a look at section 3.4. We're just going to go ahead and finish out the material for the week. And again, we'll just kind of be available for questions. Okay. So then this last section is going to be section 3.4, additional topics in probability and counting. Okay. So section 3.4 objectives, how to find the number of ways a group of objects can be arranged in order, how to find the number of ways to choose several objects from a group without regards to order, and how to use the counting principles to find probabilities. Okay, so I actually like to share, to go do the following story. Or it's not really a story. It would be better if we were engaging with each other. Let's use a different color. Okay. So now, say we consider the letters. This first, is it gonna let me? Oh, is that too far over? Oh, okay, I can't go past there. I see. So say we consider the letters. This first story is called words, right? Say we have the letters A, B, and C, right? So we want to see how many two-string words, so words made out of these two letters, can we create with these three letters, right? So how many words can we create? We can do the word AB, which is like an ab, okay? If we switch that around, is that the same or is that different than BA, ba? Yeah, that's a different word, right? AB is an ab versus BA, ba is like a sound that a sheep or a goat makes, right? So these are two different words. We can also do AC, that's a word, and we're going to consider that a word. And if we reverse that order, we're going to consider CA also a word. And then we can also do BC and CB, okay? So these are all the words that we can create of two-string words using these three letters, okay? So notice that we have a total of 6 words. That's not a 6. We have a total of 6 words here, okay? But then let's do the next story is about teams. So say we were doing like Avengers, right? So say we have what? Ant-Man, Black Panther, and Captain America, right? So this question is, even though we still have three options here, we want to see how many teams of two can we create using these three Marvel Avengers or Marvel characters. So how many teams of two can we create? Well, we could have what? Ant-Man and Black Panther. Now, if we switch that order to B and A, is that the same team of two or is that a different team of two? That's going to be considered the same team of two, right? So let's get a distinct different team of two. Another team of two could be Ant-Man and Captain America. And again, if we switch the order, it's still going to be the same two people. And then the final team of two, it can be Black Panther and Captain America. Okay? So these are all the teams of two, so we can create three teams. Okay? So with this context, notice that in either case, we had three options taken two at a time. The first one is an example of what we call a permutation where the order is important. The second example is called a combination where the order is not important. Okay, so I'm going to clear this out. Okay, so now let's look at this. So again, a permutation is going to be an ordered arrangement of objects. Again, the order is important. The number of distinct permutations of n distinct objects is going to be n factorial. So the exclamation mark is a mathematical function. It just means take that number times the number before it times the number before that and keep going until you get all the way to 1, right? So that exclamation mark is called factorial, and this is what it means. By definition, 0 factorial is going to be 1, okay? So we're just, by definition, we're going to let 0 factorial be 1. So for example, 6 factorial is going to be 6 times 5 times 4 times 3 times 2 times 1. I think the next one is if we do 4 factorial, it's going to be 4 times 3 times 2 times 1. Okay. Let's see. What's my time? Okay, I think we're okay. So the objective of a 9 by 9 Sudoku number puzzle is to fill the grid so that each row, column, and each 3 by 3 grid contain the digits 1 through 9. How many different ways can the first row of a 9 by 9 be filled, right? So with something like this, you know, we have slot 1, slot 2, slot 3, 4, 5, 6, 7, 8, and 9, right? So how many choices do we have to choose from in that first slot? If we're doing the digits 1 through 9, then we have a total of 9 choices. So we choose one of those digits and we put it into that first slot. So then once we've chosen one digit there, how many choices do we have remaining for the second slot? Well, we have 8 there. We choose and we put that there. Now how many remain for the third choice? It's 7, 6, 4, 3, 2, 1. Okay. So then what do we do with these numbers? We actually multiply. This is going to be 9 factorial and then whatever that answer is. So the number of permutations is going to be 9 factorial, which is just 362,880 ways. Okay. So the permutation of n objects taken r at a time is going to be the number of different permutations of n distinct objects taken r at a time. Oh, why did that display like that? But that's okay. And I can't change it right now. So in PR, we have this formula. I'm going to provide an analogous to this, okay? So let's see. Find the number of ways of forming 4-digit codes in which no digit is repeated. So how many digits do we have? We have 10 digits. Permutate 4, right? So it says find a number of ways of forming 4-digit codes, okay? So let's see, we have the first slot, second slot, third slot, fourth slot. How many digits do we have to choose from for that first slot? Well, we have 10 choices here. We choose one. Then the question is, how many do we have remaining for the next one? Let me see, it says no digit is repeated, right? So we have 10 options for the first one. Once we choose one, we can't use that number again. So that means we have 9 remaining for the second, 8, and 4. All right. I got it all the way down to that last one. I'm totally like not here in my mind. That's not a 4. That's going to be what? 7. Right? So 10p4, the way I'll do it, 10p4 to me means take the larger number, which is the 10, and start doing your factor. Start doing the factorial, but you only go out 4 spaces. The second number tells you how many spaces to go out. So 10p4 means 10 times 9 times 8 times 7, and we stop. All right, whatever that number is. So we have 10 objects permutated within chosen, taking 4 at a time for permutation where the order is important. Because if a code, if we take one of the codes and if we change the order, is that the same code or is that a different code? That's the same code. Sorry, that's a different code if we change the order. So that means we're talking permutation. So we need to do it in this fashion. Okay. Let's try another one. I'm going to clear the sink. So 4 digits from a group of 10. So N is 10 and R is 4. Then we have, and you see, using the formula, now the formula has 10 factorial divided by 10 minus 4 factorial, which is 10 factorial divided by 6 factorial. But then 10 factorial is 10 times 9 to 8 to 7 to 6, all the way down to 1. So the 6 through 1 on top cancels the 6 through 1 on bottom. And then you see the 10, 9, 8, 7, and that's what we literally just did. That just happened. Okay. I think I get like even more loopy when I'm like sleepy, and like I don't know, I just got sleepy. So, but we're gonna go ahead and work our way through this, so that way we'll at least be done for the week for this course, and we're gonna keep it moving. And then again, we're just gonna be available. Oh no, that's not supposed to be showing. That's okay. So it says each year 33 race cars start the Indianapolis 500. How many ways can the cars finish first, second, and third? Right. So if we have first place, second place, third place, right? We're going to say first, second, and third. All right. It says we have 33 cars. So how many choices do we have for first place? We have 33 choices. Once we choose somebody, how many are left for the second? Then we have 32 for second and 31. So this one is actually going to be 33p3. And you see the 33 times 32 times 31, which is the same as what we have, and we get to 32,000. I'm gonna clear these markings. Okay, we're gonna let that be. So the number of distinguishable permutations of n objects where n1 of one type, n2 are of another type, and so on is going to be given by this. Okay. Let's see this in action. So it says a building contractor is planning to develop a subdivision. The subdivision consists of 6 one-story houses, 4 two-story houses, and 2 split-level houses. And how many distinguishable ways can the houses be arranged? So we have a total of 6, 10, 12. We have a total of 12 houses. Then we have 6 of the first type. So that one's going to be 6 factorial, 4 of the second, and 2 of the final. And we're going to get something like this. Okay. I'm going to let that be for now. So if you are using a graphing calculator, you can actually use factorial in your graphing calculator and it'll work. Something bite me. No. All right. Oh, so those are discussions on permutations. Next, we want to look at combinations. That was like the team example that we did. So combination is actually the exact same as permutation. We just have to remove the repeats, right? So we can actually do the same process as permutation, but once we identify it as a combination, we have to remove the repeats. We remove our repeats by dividing by r factorial, right? So the combination is actually just a permutation divided by r factorial. So a state's Department of Transportation plans to develop a new section of interstate highways and receives 16 bids for the project. The state plans to hire 4 of the bidding companies. How many different combinations of 4 companies can be selected from 16? So they're asking us to calculate 16 choose 4. I literally just said that this is the same as 16p4 divided by 4 factorial. So 16p4 means we're going to say 16 times 15 times 14 times 13. So we started at 16, we start counting down, we only go out 4 spaces in this case. And then 4 factorial is going to be 4 times 3 times 2 times 1. We just have to crunch that number. Okay. Okay, so you see it here. Let's see my time. Okay, I think I'm okay on time. So summary of accounting principles. I'm going to let you go through this on your own. Let's look at this example. It says a student advisory board consists of 17 members. 3 members serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve any of the positions. What's the probability of randomly selecting the 3 members who will be chosen for the board? Okay. So we have the chair, secretary, and webmaster. So we have a position for the chair, secretary, and the webmaster, right? So how many choices do we have to go into this position of chair? Is 17. Once we choose somebody for the chair, how many are left for secretary? Is going to be 16 and then 15, right? So given the 17 members, arranging them in these 3 slots, these are permutations where the order is important because that determines what position you're in. So then it's going to be calculated in this fashion. So now say we have where A is the chair, B is the secretary, and C is the webmaster. The probability of choosing that is just going to be 1 out of, let me think about it. 1 out of the total number of outcomes. So then of choosing the very specific one, there's only 1 outcome out of a total of whatever this number is, 17 times 16 times 15, whatever that number is. Okay, let's see it over here. Order is important, so that means we're talking about a permutation. There's only 1 favorable outcome, so there are 4,080 ways that the 3 positions can be filled. But again, we only have 1 favorable outcome, so that's going to be 1 out of that 4080 if we wanted to choose this specific outcome. Okay, we're almost there. Keep in mind, in Excel, we can also do some of these calculations. We're asked to find the probability of being dealt 5 diamonds from a standard deck of 52 playing cards. Okay, so 5 diamonds, right? If we have the first one, second, third, fourth, fifth, right? Let me think about something. So, yeah, why are we drawing a blank? I think it's because I'm sleepy. Let me think about it. Give me a moment. I want to think about what I want to say. Oh, okay. So we have these 5 slots, so we want to find 5 diamonds, right? How many diamonds do we have to choose from? Well, if we restrict it to diamonds, we have 13 diamonds. So we choose 1, right? It's 13 cards in a suit. Is that how you say that properly? 13 denominations in a suit. So we have 13 diamonds to choose from. Then we have 12, and then 11, 10, and 9. So if say we have these 5 cards, A, B, C, D, A, B, C, D, E, right? Say we change the order. Are these the same 5 cards or they're different? These are considered to be the same. So we're doing a combination. Okay. So then we're going to have 13 diamonds to choose from, taking 5 at a time. But if we want the probability, we need to do it over the total number of outcomes. So that means we have a total of 52 cards, taking 5 at a time. Yeah, I think this is okay, right? So I'm going to clear this out. And, well, we can show that calculation really quick. I think we have it here, though. I'm just going to clear this out. So in the standard deck of playing cards, 13 cards are diamonds. No, it does not matter what order the cards are selected. So the possible number of ways of choosing 5 diamonds out of 13 is 13 choose 5. Again, if we have 5 cards and we change the order, it's still the same 5 cards. So that means the order is not important. That means we're talking about a combination. But then, so the probability of getting 5 diamonds, the top number restricts it to just the diamonds. The bottom number considers all the playing cards. So we got to say the diamond suit versus all, and we get this probability. A food manufacturer is analyzing a sample of 400 corn kernels for the presence of a toxin. In this sample, 3 kernels have dangerously high levels of the toxin. 4 kernels are randomly selected from the sample. What is the probability exactly 1 kernel contains a dangerously high level of the toxin? Let me think about this one. Food manufacturer, 400 kernels for the presence of a toxin. In this sample, 3 kernels have a dangerously high. It says 4 kernels are randomly selected, right? What's the probability that exactly 1 kernel contains a dangerous? So we're asked to find the probability of 1. I guess I could have gone with it. But we're asked to find the probability of having 1 dangerous kernel, right? So what does this outcome look like? This outcome is going to be, if we choose 4 kernels randomly, that means we're going to have 1 dangerous kernel and the other 3 are going to be good or not dangerous, right? So then say we focus on what's the probability of 1 of the kernels being dangerous. How many dangerous kernels do we have? In example, 3 kernels have a dangerously high toxin, right? So we're going to say 3 choose 1. This is another way we write combination. We have 3 dangerous kernels chosen 1 at a time, times how many good kernels do we have? So if we have a total of 400 and 3 of them are bad, that means we have 397 good kernels taken 3 at a time. But then we're going to say divided by, keep in mind that probability is always between 0 and 1. We got to consider all of them, not the separate cases, right? So then we have 400 kernels taken 4 at a time, right? So these are all combinations. Okay, so then the first one is going to be 3. You know how to calculate combinations. The main part is setting this up there, all right? So just for the sake of time, I'm not going to crunch those numbers. We're going to look at it over here, though. So it says the possible number of ways of choosing 1 toxic out of 3 toxic is going to be 3 choose 1. We have the 3 toxic taken 1 at a time. Possible number of ways of choosing 3 non-toxic kernels from 397 is going to be 397 choose 3, this 10 million outcome that you see here. So then using the multiplication rule, we get something like that. But if we want the probability, we got to consider the number of possible ways of choosing 4 kernels from 400. So we would say 400 choose 4, we get this. And then now you see here what I had on the previous slide. The way I had written that combination, that's called the binomial coefficient. Because this discussion actually has applications to the expansion of binomials, like x plus y to certain powers. We can actually use, there's a pattern to the expansion of binomials, but yeah, okay. And I think that actually brings us to the end of the material for the week. So with that we're going to, so we've at least done the video lecture. We have the lectures available for 3.1 for all of chapter 3. Just kind of monitor your GMC emails and any assignments that you see on Pearson. You want to get those submitted. I'll be updating our grades on Moodle shortly. I've calculated week 2 grades. I just need to update our Moodle page. One of my courses was giving me a hard time, so I'll probably be doing that later today. I need to do one more lecture, and then yeah. So, but yeah, I'll be available throughout the day. You can honestly just call me throughout the day, or call my office phone, or email me. I'll just be monitoring these sources and replying to requests. Okay. And so, on that note, we're going to actually end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace. You just need a little bit of energy. All right.